अच्छा, what were we up to? We were क्या कर रहे थे? अच्छा, this one. I think we had done just electrophilic substitution of benzene, right? And उसमें था कि we did the whole electrophilic substitution of benzene and nitration and the chlorination and bromination of benzene. Okay, there was nitration of benzene as well. So what we had started with was that we had started doing electrophilic substitution of benzene derived compounds or benzene derivative compounds. And there were two types of groups. Either मैं add करूं this. You had the electron donating groups and you had the electron withdrawing groups. So these ones had slightly slower reactions. Okay, so you had two types of groups. You had electron donating groups, which would donate electrons, and electron density would increase at positions 2, 4, and 6. Okay, so the electron density at these positions was higher. So your electrophiles would get attracted to positions 2, 4, and he gets 6 and 2 are kind of the same position. And your electron donating groups, let me highlight that. ये सारे. अच्छा, so your electron donating groups were alkyls, phenols, amines, chlorine, amides, right? So the first one I think we did, that was arenes, which were benzene plus an alkyl chain. That was done. Then we did, so that one was done, and I told you that, so usme I had told you that your, if you do bromination, it's going to be exactly the same conditions. You get no different, everything would be exactly the same, except that the electrophile Br+1 would get attached to positions, either to position 2 or to position 4. You get 6 is kind of the same. So then we did nitration. The conditions were exactly the same. All you had to be careful about was that the NO2 would get attached to positions 2 and 4. Okay, that was what we did. And then this was another electron donating group. Okay, we had started with phenols, which was benzene plus an OH group. And remember, that is not an alcohol. मेरी आवाज lag कर रही? Ishaq, can you cast?
No. Yeah, it's fine.
ठीक है. So hala, I'll send the recordings as well. ठीक है. तो मेरा इंटरनेट सही चल रहा है, ठीक है. I'll send the recordings to you. इसके end पे all of them. अच्छा, anyways, ये कर लेते हैं. We'll keep it short then, because I know internet is like really bad everywhere at the moment. I said this one, we will start with phenols and electrophilic substitution of phenols. ठीक है. Now the thing is, the phenol is an electron, the OH is an electron donating group as well. It's a 2,4 directing group. The lone pair on oxygen, it overlaps with benzene's pi electron cloud, okay, over here, and it increases the charge density, and all the other electrons, they get repelled, and they all gather on the other side. Okay, so the electrophiles are going to get attached to positions 2, 4, and 6. Now the thing is that this OH group has a compared to arenes, it's significantly electron donating. Okay, so its effect is stronger. So it's a strongly, because it's got a whole lone pair that it can donate. Oxygen has a lot of lone pairs. It's got 2 lone pairs. So it's a strongly electron donating group. So what happens is, that the charge density on the benzene increases significantly. Not just slightly, it increases significantly. And specifically on positions 2, 4, and 6. He gets 6, I'm putting in brackets. So charge density on benzene at 2, 4, 6 increases. It increases significantly. And now the conditions would change. The reactions are pretty much the same. It's the same reaction, except that the conditions are going to be a lot milder. Because of that, because of this thing, electrophiles would be very strongly attracted. They're going to be very strongly attracted, and therefore no catalyst is required in either nitration or bromination. The entire, because remember, benzene ke saath, the problem with benzene was that it failed to polarize the molecule of bromine, right? The double bond electron density over here in benzene was very low. The charge density was not very high because the p orbital was overlapping on both sides. Its electrons were getting distributed and overlapping with the p orbital on the bottom and also on the top. So the charge density was very low, which is why the bromine molecule was not polarized a lot, which is why you needed a catalyst at the other side that would increase the polarization, which would not be the case with phenols. In phenols, you don't need a catalyst. So if you go back to phenols, the main difference is no catalyst is required. Okay, so here's my phenol, and if I do bromination, here's the OH. Okay, so for bromination, everything would be quite simple now. The only thing that's required is Br2 aqueous. No catalyst needed. And the other thing is that the reaction is going to be very fast as well. So what happens is that not only would one bromine get attached, in this case, it's going to be 3 bromines that will get attached to this. There's going to be a bromine that's going to get attached over here, one getting attached on the 4th position, and one of them getting attached on the 6th position. So you're going to get bromine on all the positions. So bromine getting attached on all 3 positions. This is what you're going to get. And plus there would be 3 HBr molecules that will be, because the H is going to get knocked out from the benzene. So you're going to get 3 HBr molecules. And this thing is called 2,4,6 tribromo. Phenol. So highly activated phenol. Is bromination clear? Ye clear? Qasim, Isaac, Ibrahim, is this clear? That bromination
Yes.
in phenols. So now the next thing is nitration. That will be very fast as well. And you don't need a catalyst. You can remember in the previous case, the NO2 plus 1 electrophile had to be created. So same with Cl2. With Cl2, it's going to be exactly the same. So so for chlorination, it's going to be exactly the same. Except nitration, what's going to happen with nitration is that you can either use, remember the previous nitration of benzene. If you go back, so this was bromination. When we did nitration, there was a reaction first where concentrated sulfuric acid had to be added, and you had to add nitric acid, and the NO2 plus 1 electrophile had to be created first. And then that NO2 plus 1 electrophile would attack the benzene and get attracted to the benzene electron cloud, bond with one of the carbons, and the H would then leave its electron, so the benzene electron cloud becomes complete. And the H2SO4 was acting as a catalyst. It was enabling the reaction. It was helping us create the NO2 plus 1 electrophile. Now you don't need a catalyst. ठीक है? इस case में what's going to happen is that even if you use dilute nitric acid, you don't even need any conditions. Dilute nitric acid, no sulfuric acid or catalyst is required. You get no catalyst needed, and you're gonna get two compounds. You can remember 2, 4, 6 positions. So you're either going to get an NO2 at position number 4, which is this position, or you're going to get an NO2 at position number 2. So there is this one is 4-nitrophenol, and this one is 2-nitrophenol. But there's another reaction, which is that if you use concentrated nitric acid, then what happens is that the NO2 would get attached to all 3 positions. So you will get NO2 on position number 4, on 2, and this is 4. And you'll also get an NO2 at position number 6. So this is concentrated nitric acid. I mean, if you use that. And that's 2,4,6 trinitrophenol. So 2, 4. Now there are 3 nitro groups that are going to be attached. So is this clear that no catalyst required in the other one as well?
Yes.
And needed in the other one as well. So those are your reactions, and you got to remember these reactions of phenols. This is this one is nitration, and that's your bromination. About this 2,4,6 tribromophenol, they would ask you about the observation. The first observation is that the Br2 gets decolorized. The second observation is this 2,4,6 tribromophenol is a white precipitate, and this is often used as a test for phenols. So this one is going to be used as a test for identifying phenols. So keep that in mind. Anyways, the thing is, phenols are, I mean, that pretty much sums it up. Phenols, Keep this in mind that phenols are highly reactive and they don't need a catalyst. So there's going to be some very little difference between the conditions. And the bromine or the NO2 group would like to get attached on all three positions. Okay? Clear? Is this clear?
Yes.
Yes, sir.
So okay, there's a last one which is phenylamine. It's basically exactly the same as phenols. So I'm just going to make a note that so with phenylamine and the electrophilic substitution, you get all that we're going to state is that it's exactly the same as phenols. Because they also have. So what are phenylamines? Phenylamine is this thing. It's a benzene with an NH2 group. Okay, phenylamine is it's got a lone pair, and exactly the same thing happens. The lone pair overlaps, and you get a much higher electron density at positions 2, 4. The other electrons they all get repelled, and they accumulate on the other side. Okay, so it's exactly the same as phenols. So just keep that in mind. You're going to get the same exact reactions. Everything will be the same. You get a question on this, which is why, I mean, you get this specific question, which is why is a catalyst not used for phenols or phenylamines, or why are the reactions faster? So the answer to that question is that, I mean, the way you're going to write the question is, the way you're going to write the answer is that the lone pair on oxygen in OH, or in the case of phenols, it's going to be on nitrogen in NH2. On nitrogen. It overlaps with benzene pi electron cloud. Which increases its charge density. And leads to stronger attraction for electrophiles. So it's got a much higher polarizing power as well. So it is capable of pulling out the bromine +1 or the NO2 +1 from directly from, you don't need any help. The reaction will happen on its own. Okay. So that's all about phenols and phenyl amines. And that's pretty much all about 2,4,6 directing groups. Now there's another one which is the opposite, which is 3,5 directing groups. You don't need to know any details about that. Okay, so 3,5 directing groups. which are basically your electron withdrawing groups. All you need to know about them is that the reaction are slower. No details required. No specific details required. Reactions are slower. Or you can say benzene is kind of inert because it's going to have a lower charge density. So benzene is unreactive towards electrophiles. So for example, I remember we did C5 directing groups before that. We wrote down a whole list, TK, which is over here. If you look at the C5 directing groups, these are all electron withdrawing groups. What would happen with C5 directing groups is that over here, the electron density was actually higher on positions 2, 4, and 6. On the other one, the electron density is actually going to be lower at positions 2, 4, and 6. NO2, that's an electron withdrawing group, NH3 plus 1, CN, aldehydes, ketones, or carbonyl groups, carboxylic acids, they're all electron withdrawing groups. So if that is attached to benzene, तो काम उल्टा हो जाएगा, ठीक है? If that is attached, so for example, I have an aldehyde attached. That's an electron withdrawing group. It's going to withdraw electrons. So your electron density at this position is going to be lower. And since overall the electrons are getting pulled towards the right side, the electron density is also going to be lower at this corner over here as well. So exactly at those positions, because all the electrons are getting pulled to that side. So in this corner on the extreme opposite side, the electron density is going to be lower. And obviously these electrons over here, they're being withdrawn or getting pulled towards the oxygen. So they would be, the charge density would be lower over there as well. So by default, although electron density is not higher, but relatively it's going to be higher at positions 3 and 5. ठीक है, वो count कर लो, it's going to be 3 and 5. So that is what's happening. All you need to know is that if electrophilic substitution is done, ignore the conditions. So if you do electrophilic substitution, remember the electrophile, let's call it X plus 1, will get attracted or will bond to positions 3 and 5. That's it. Okay, so whether it's, so you have to remember what those groups were. Okay, there were carbonyl, there was carboxylic acid, there was कौन से groups there? They were, let's write those down. C5 directing groups. You had NH3 plus 1, carbonyl groups, CHO, that's aldehyde, carboxylic acids. Okay, there were esters. There was NO2 as well. All of these will prevent or will stop electrophilic substitution because they'll decrease the charge density. ठीक है? तो यहाँ पे overall ठीक है? Is this clear?
Yes.
Yes.
So there's still something. So remember, electrophilic substitution is something that's big in A-levels organic. I said the last thing that you're going to do about electrophilic substitution is that's alkylation and acylation. So we're going to do with, the mechanism and the conditions are not really, actually they are kind of needed. The mechanism is exactly the same. So alkylation of benzene. So alkylation is when you want to attach a carbon chain to benzene. So alkyl chain is attached. So it's basically and the benzene basically turns into an arene here plus alkyl chain. So kind of similar conditions. So you've got a benzene. Here is the ring, and let's say there's a halogenoalkane. Normally, it's going to be a chloroalkane. So you've got a chloroalkane. So this carbon over here has a partial positive charge. If it's got a partial positive charge, the benzene electron cloud is going to get attracted to this, and similarly, the Cl electrons are going to be repelled. But normally, benzene does not have a lot of polarizing power, which is why. So if you remember nucleophilic substitution reactions as well, halogenoalkanes would always react this way. The positive carbon will attract the electrons, and the Cl will get knocked out. So as a result, what will happen is in that particular carbon, you have to spot the carbon that's got the halogen. That's the one that's going to get attached to benzene, along with the whole thing. Okay, so this part, whatever's after that, the entire thing will get attached. The Cl will get knocked out. Okay, that's the reaction. And since benzene is not very reactive, you would need a catalyst, which is going to be FeCl3 or AlCl3 catalyst. Okay, clear? This is exactly the same way the previous electrophilic substitution, all the previous electrophilic substitution happened. Okay, ये clear है? Ibrahim clear? Qasim, is this clear?
Yes.
And you will also have HCl as a byproduct. The only difference is that the entire carbon chain is getting attached to it. It's just like nitration. It's just like bromination. So this is alkylation of benzene, and similarly, you're going to have acylation of benzene as well, which is kind of the same. TK, except that's with an acyl chloride. So what's an acyl chloride? Well, the work here. So I'll just copy paste the entire thing. Actually. So we're going to do, instead of alkylation, we're now going to do acylation. So it's not going to be an alkyl chain. This thing is not going to be produced. the difference is going to be that it's a reaction with acyl chloride, and acyl chloride is this thing. It's got C double bond O. You get the carbon is partial positive. So it's like a carboxylic acid, but with C double bond O and Cl. This is called an acyl chloride. And in a similar way, just like the previous case, this thing over here is going to get attached. You get the C double bond O is going to go and going to get attached to benzene. So we're going to correct that on the other side. So it's just going to be C double bond O and Cl. That's going to get attached. That's it. Okay. And you have FeCl3 or AlCl3 catalyst, which is exactly the same. So these are your last two electrophilic substitution reactions. Ye clear? Is this clear?
Yes, sir.
So brief summary is, I say last two gonna just let me double check this के इसी में heat तो required नहीं है. Just 1 second. एक second, let me just check the latest market scheme. नहीं वो किधर है? Syllabus का है. एक second. ठीक है. Syllabus में heat is required, so there's going to be heat, and there's going to be heat over here as well. Plus, the proper name for this is Friedel-Crafts alkylation. Or acylation is a proper name, and that's again Friedel-Crafts. अच्छा बाकी ठीक है. Both of them it's heat, and the rest is like phenols का मैं थोड़ा सा चेक कर लूं कि एक पार्ट कंप्लीट हो गया. ठीक है. that's अच्छा phenols आ ही नहीं रहा. एक सेकंड. पहले ठीक है. just give me 1 second. तो ठीक है. we're done. हाँ phenols आया. एक सेकंड देना मुझे. ठीक है. PR2 वाला 246 ट्राइबर. Yeah, that's fine. चलो ठीक है. ये सारा हो गया. I'm going to send these notes. और इनको go through कर लेना. It's all about electrophilic substitution. That's one chunk. ठीक है. We're done with one basic part. अगली क्लास में we'll do past papers of this. ठीक है. चलिए क्लियर है. कोई ये फिर नेक्स्ट क्लास में कंटिन्यू करते हैं. ठीक है.
Okay, sir. Last.
ओके. अल्लाह हाफिज.